Thank you for downloading this podcast from The Really Clubby Show on Talk Radio 702 and 567 Cape Talk. For more, please go to 702.co.za or capetalk.co.za. Talk Radio 702 and 567 Cape Talk. The Naked Scientist.
Chris Smith, good morning.
Good morning.
Where in the world are you, sir?
Well, I'm sitting in a studio in sunny Cambridge in Britain, which is about 50 miles, 100 kilometres or so, 80 kilometres more accurately, north of London. And it's a beautiful day. It's almost as good as the South African weather I was experiencing last month in Joburg.
Well, we're having a fantastic week this week, I'll tell you that much. Now, before we get to all the calls, and get your calls in right now, 011-883-0702, Cape Town, 021-446-0567, the Naked Scientist standing by to field all those questions. Just one I want to throw your way, Doc. As the medical field, we've been able to grow skin cells for decades now. So what is so unique, so special about this new discovery in the UK?
Yes, some researchers at King's College in London, this is Anastasia Petrova and her colleagues, they have managed to produce skin in a dish that is the full thickness of human skin and all of the layers. When you look at the literature, you'll see that people previously have grown skin cells, and this usually ends up being a sort of flat sheet of cells that don't have this very specialised structure that skin does. If you were to take a biopsy or a sample of human skin and look at it under a microscope, you'd see that at the very bottom there were these stem cells that are dividing very fast, and then they produce a basal layer of cells, and they specialise a bit more, and then they slowly become flattened, and they fill up with a protein called keratin, which makes them tough, and then they dry out and die and form this outer impermeable layer. And that is really special because it keeps bugs at bay, it keeps our water in, it keeps chemicals out. And if we want to test various drugs and cosmetics and other chemicals, actually we've got no way of doing that really on proper analogues of human skin apart from to use either humans or animals. But with this new discovery, what they were able to do is to take either embryonic stem cells or take cells and reprogram them from an adult to think they're stem cells again, and then grow them in the dish with the right environment. So you put the right cocktail of growth factors in there and the right level of oxygen and water, and the cells are fooled into thinking they are back inside a baby, developing the outer skin of a baby, and they form skin in the dish, and they form these proper successive layers of skin with this specialisation from the bottom up. And so what they're saying is they can now produce these layers of skin, and we've got a really nice model against which we could test various chemicals or drugs for skin conditions, drugs for other conditions to see how well they get through skin, so we wouldn't have to give injections, we could use patches and so on.
So no more monkeys in cages?
Well, monkeys are very expensive, actually. Most people work on things like rabbits and mice because they grow very quickly, they mature very quickly, and they reproduce in large numbers. But ideally, no one wants to work on any kind of animal if you can avoid it because, A, there's the ethics and morals to do with that. Not everyone agrees with that. But B, it's really expensive. I mean, not many people realise that to keep a mouse in a cage in a laboratory costs more than to feed a human for a week. It costs between £5 and £10, in other words, more than 100 rand a day to keep a mouse in a cage in a laboratory. One mouse. Gotcha. And mice don't eat very much.
All right, now we're going to go from mice to flies. Ross, your question. Good morning.
Yes, I'm afraid this beautiful weather we have in Cape Town also brings some problems, and it's flies. Now, over the years, a few years ago, I could whack flies dead easy, and they were quite easy victims. I've found now, with the passing of years, that flies are far more difficult to plop, as we say. And I'm wondering whether it's a superfly or something is being bred into the system.
Before we go to Chris, is it not just a case of you getting a bit slower, Ross?
I didn't want to hear that. Yeah.
Let's check your superfly theory, Chris.
I'm really glad you said that, not me, because that was going to be my speculation, but now I don't have to. I haven't heard of a breed of superfly which are suddenly much better at being swat resistant, and I would think it's possibly that your own reactions, maybe the light is different, or maybe you are just a little bit older, and this is meaning that you're slightly less adept with a tea towel. But on the other hand, people have studied how flies seem to be able to elude the swatter so well, and that they do have these nerve circuits which are wired up between their visual system and their motor system, so that they very quickly react to what they perceive to be a looming threat, and they ping themselves off of whatever surface they're sticking to at the time, and then launch themselves into flight. And this is a fast reaction in the flies using very fast and very few nerve connections, because the more nerve connections you make, the slower the message is in getting through. And these flies have a very fast motor system which relays a stimulus directly from their visual system straight into their muscles to make them fly off. And so flies are very good at escaping for that reason. And it may be that as I say, you're not quite so adept with the tea towel these days as you were, or that that you're just finding it harder to spot the flies because maybe the light's not so good in your house, or the flies are landing on something else.
Or maybe I'm developing more nerve centres, so it's taking longer for the messages to get through.
Oh.
There you are.
You think you're being hyper-connected. There you go.
Yes.
Ross, I think you may just be getting a little bit slower. Wax on, wax off, Danielson, if you know what I mean. Ross in Thornton, thank you very much for that. Barney in Brakpan, good morning.
Hi, good morning, gentlemen. Dr. Chris, my question this morning is two microwave-related questions. If I put a 500-gram steak in the microwave and warm it up for 30 seconds, then it's normally the perfect temperature for me to eat. But if I put, for example, two 250-gram steaks, then it's not the right temperature. And that is putting it next to each other. I would understand if I had the one on top of the other one, that the one below might have been not as heated up as what I would have liked. And the same thing. This is the second question, and then I'm done. And the same thing with pumpkin and spinach I've picked up as well. Put it in the same bowl in the microwave, 10 seconds, 15 seconds. Then it's the right heat. But put a 250-gram steak in the same plate with the pumpkin and the spinach, then the vegetable it's completely cold, and just the meat has been heaten up.
Okay.
And that's always fascinating for me, and I just want to understand why that happened.
Thanks, Barney. Listen on the radio, please. Chris?
Hi, Barney. Well, the answer to this, first of all, in the world of physics, there's no such thing as a free lunch. Since you're cooking food, I thought I'd use that terrible analogy. And when you put food in the microwave oven, it's converting electrical energy into microwave energy. These are electromagnetic waves. And the microwave can only add energy at a certain rate to the food. So the more food that you put into the microwave oven, the more water, because it's the water molecules largely that soak up the microwave energy, the more water there is going in, and therefore the more surfaces, the more volume there is to absorb energy. And since the microwave oven can only deliver energy at a certain rate, the more things there are to soak up that energy, the slower the temperature must rise of all of the food. So the more food you put in, the more you've got to heat up, because the energy is shared amongst all of the things you put into the microwave oven, and therefore your steaks are going to take twice as long to cook if you put twice as much meat in there. Now, the pumpkin versus meat story, the answer to this question is probably the following, that when you put something into the microwave oven, the water molecules absorb the microwave energy, and they try to vibrate or shake at the same rate as the microwaves are whizzing backwards and forwards in the microwave oven. And microwaves produce about 2.5 billion of these waves every second, which are whizzing backwards and forwards. So the water molecules are trying to vibrate at that rate. The more water that there is in something, the more of these microwaves it can absorb. And also, the more salts that there are in there, the better it's going to absorb the energy, because the salts also create currents, which can, again, absorb energy. And steak is very salty because it's animal cells, there's enormous numbers of salt particles in there, and I think it's probably a lot saltier than your pumpkin would be. And for this reason, I think that the steak will probably absorb the energy at a faster rate because it's very salty water compared with the pumpkin, and therefore it will differentially heat up faster than the pumpkin because more energy, relatively speaking, is going to the steak weight for weight than the pumpkin, and that's why one will appear to cook before the other. You can get the same phenomenon if you put your jacket potato and a slice of bacon into the microwave together. The very salty bacon will end up frizzled up to a black piece of carbon before the potato is even halfway cooked, and that's for the same reason, I think.
Got you. 13 minutes to go before 10. The Naked Scientist with you until 10. Get your calls in. We'll deal with more of them after the break.
Talk Radio.
Talk Radio 702 and 567 Cape Talk. The Naked Scientist.
Udo and Faridi Klabi, we're with the Naked Scientist. Back to your calls. Chris, I've got one on SMS. Yes, Penny wants to know. Please ask Chris, if a person is allergic to penicillin, can they still eat blue cheese?
Yes, they don't seem to have a problem with that. Penicillium is a big family, but the penicillium which is used to produce penicillin, the actual drug molecule, doesn't seem to cause too much of a problem with people actually having cheeses. There are some cross-reactions with other antibiotics that are similar-shaped molecules, but not with cheese, as far as I know.
Okay.
It's a nice question. I'll do some probing just in case I'm wrong on that one, but I think you're fine with your cheese.
So Penny,
please carry on enjoying that delicious blue cheese, which I love.
I was going to suggest she holds off on the blue cheese until you come back and let us know next week, perhaps.
Well, I wouldn't want to deprive someone of one of life's pleasures, but I will certainly see if penicillin means that blue chease is off the menu. Let me go and check.
Chris is checking. Penny, thanks for the question. Richard in Parktown, good morning.
Morning, Chris. Hi.
Hi.
If nanotechnology is all about trying to understand and to study the infinitely small, aren't we ourselves less than nano in terms of the known universe and the possibility of the infinite? I mean, is anybody besides religions trying to understand what nano man is actually worth, or what is the value?
Yeah, I think your point, Richard, is that we think of ourselves as the be-all and end-all. And, before Copernicus came along, we thought that the world did quite literally revolve around us. The whole universe was revolving around us. Now we know that's completely not true. We know we're one tiny, tiny speck in the middle of a very massive ocean. There are something like a sextillion, which is probably 22 zeros, I think, after a 1, numbers of stars in the known universe, and each of those might have, say, 10 planets, so there's probably 10 to the 23 planets out there, and some of them are going to be like our own. We're just on one of them, so we're one part of a very, very big number. And obviously, the smaller you look, you see that this whole idea of even fleas have fleas is true. We've found in recent years that viruses even have viruses that prey on viruses. So, we catch bacteria, we catch viruses, but bacteria catch viruses, and there are even viruses that eat those viruses. So the smaller you look, the smaller and more complex things become. It's rather like a fractal, isn't it? But I think we are at the limit with what we think we are with particle physics. If you ask the scientists at CERN who are smashing things together with their very powerful particle accelerators, I think they're pretty comfortable that they don't believe that we can go much smaller than the particles that we now understand make up the standard model, with one or two gaps, such as the Higgs boson, which they now think they've found. So I think we have reached potentially the size limit, but we certainly haven't explained the extraordinary relationships between a lot of these particles and the really weird things, such as why it is that the charge on an electron precisely balances out the charge on a proton, for example. And we still haven't got to that sort of level of understanding, but they're working on it.
Now, for me, the simplest questions are always the best. Fabrizio wants to know, why are clouds white?
Well, this is all about water scattering, and it's exactly the same reason that snow is white or ice crystals are white. Water itself is transparent, but when water freezes and it forms water, tiny particles of ice, which is water molecules glued together into a solid, then what you've got is lots of surfaces. And when a light path or series of photons goes into ice or snow or a cloud, because that's ice particles or water droplets as well, whenever the light goes from one medium, air, into another medium, water, then it changes speed. In fact, it will slow down very slightly when it goes from the air into the water, because the water's more dense. When you make light slow down in this way, you also make its path bend. When you bend light enough times, because with tiny crystals, light's going to be going into air, into water, into air, into water many, many times, it will bend many, many times, and all of the colours that make up white light will be bent round and reflected back to you. So what you see are lots of different colours all coming back to you at the same time, and if you mix all these colours together, you see white. And that's why snow is white and clouds are white, but water itself appears to be a transparent colour because the light isn't doing these multiple bendings. It's going into the liquid and then carrying on in a straight line. You can make water reflect white light by adding, say, milk to it. Milk is lots of little oily particles, so there's oil blobs suspended in the water, and you can also do this with certain detergents. That means when the light goes into the water now, it goes into the water, but then it hits some oil and bends and changes direction, then goes into water, bends and changes direction. The net effect is the same. All of the different wavelengths of light are reflected towards you, and when you add all those different colours together, they mix to make white.
Tapelo in Kempton Park, good morning.
Hey, morning. I just wanted to find out, when you grow bold, what happens to those cells around the area, and why the other ones are wider than the other ones?
I hope you get that, Chris.
I don't know.
Did you say why you go bald?
Yes. The cells around the dying cells around the hair. What happens to them?
Okay, thanks, Tapelo.
Yeah, so when we've gone bald, why has the hair stopped growing in that place? Well, hair grows from structures called hair follicles, and hair follicles are specialised clusters of stem cells embedded in your dermis, which is one of the layers of the skin. And those stem cells are arranged in a sort of ring configuration, and they grow the hair as a filament by producing this keratin filament, which is what the hair's made of. And below that are some melanocytes which give colour. They add the melanin pigment to the hair to give it its colour, whether it's blonde, ginger, dark, black, whatever colour. And the hair then grows out through the skin. And for some reason, testosterone is metabolized in some parts of the scalp into a toxic chemical which poisons the hair follicles, and they die, and those stem cells are lost, and that means that the capacity to produce a hair from those hair follicles is also lost, and so eventually you go bald. But it's interesting how the distribution isn't all over the head and all at once. It is in this very characteristic so-called male pattern baldness. There's another reason why you can go bald, and that's because of something called alopecia. And this is where, for some reason that we don't really understand, the immune system can attack hair follicles, and all over the body, all at once, you lose your capacity to make hair, and people become completely lacking in hair all at once.
All right, now we literally have a minute for the question and the answer. Theo in Artery, short and sharp, good morning.
Good morning, Udo. Good morning, Chris. Chris, I'm just curious to know, fish in the ocean, when you catch a fish, you still have to salt it when you eat it. Despite it being for years in the ocean, shouldn't it be salty, the flesh?
All right, Theo in Artery, I think a question asked, yeah.
Fish are salty in the same way that we're full of salt. The amount of salt in a human is extremely high, and that's how cells work. Our cells that we're made of, and there are maybe 100 trillion cells in our bodies, they are full of salty water, and cells use enormous amounts of energy just pumping salt backwards and forwards to keep the volume of our cells correct, because salt attracts water to it, so the more salt you have in your cells, the bigger they'll be, and so cells control how much salt they contain to keep their cell size absolutely right. Fish are no different. In fact, they have a harder challenge because they live in an environment which is very concentrated in salt, so they have to be careful to keep the right amount of salt in their body to compensate for what water concentrations they have around them. So seawater fish concentrate salts in their body to pull water into their body and keep themselves at the right level of saltiness. And so that's why actually you do need to add a little bit of salt, because they regulate the levels very carefully in their cells.
Dr. Chris Smith, as always, an absolute pleasure. Thank you.
Thanks for having me. See you soon.
We'll catch you next week.